If you close your eyes and imagine a wave, you'll probably picture a beach with water crashing up on the shore. In our mind, the movement of the wave and the movement of the water are one and the same. However, this relationship isn't quite so simple. A wave is capable of traveling through a material faster than the material itself is moving. You can see an extreme example of the separation of wave movement and what it travels through by using a jump rope. You just need two people to do this experiment. Have each person hold one end of the jumping rope. One person holds still as the other moves their arm up and down in a quick motion. You can see a wave travel down the rope, but the rope itself isn't traveling along with the wave. In this lesson, we're going to learn a bit about how waves affect the material they travel through by digging into wave displacement. Before we learn about wave displacement, let's talk a bit about the concept of displacement in general. Do you remember the difference between displacement and distance? It might seem like it, but they aren't the same thing. Distance is how far an object has traveled, and displacement is a measurement of the change in an object's starting position. The best way to visualize the difference between the two is by using the example of a round trip. Let's imagine that you travel 10 miles to work or school, and then 10 miles back home at the end of the day. The distance you traveled is then a total of 20 miles, but your displacement is 0 miles. This is because you start and end the trip at the same spot, your home. So there's no overall change in position from where you started the trip. Now that we know what displacement means, what exactly is the displacement a wave causes? Let's look back at our jump rope example to examine a 2D transverse wave. In two dimensions, the only possible directions for displacement are on the same axis as the direction the wave is traveling or perpendicular to it. To simplify things, we'll call the direction the wave's moving horizontal and the perpendicular direction vertical. These can be then represented visually by the x-axis and y-axis. For the wave on our jump rope, there is only vertical displacement. What's being displaced are particles of the jump rope itself, and the rope only moves vertically up and down. Remember, the rope itself is not traveling horizontally with the wave. This means the transverse wave displacement is the change in a particle's vertical position from where it was before the wave traveled through it. Now that we know what we need to find the vertical displacement caused by the wave, how do we go about doing that? We want to find the displacement at any point on the jump rope, and the jump rope is moving in a harmonic sinusoidal wave shape. So it makes sense to use a sine function to describe our displacement. To find the displacement of a harmonic wave traveling in the positive x direction, we use the following formula. yxt equals a sine kx minus omega t. For a wave moving in the negative x direction, you simply change the subtraction sign to an addition sign. There's a lot in this formula, so let's break down the different pieces. The displacement, yxt, is a function of the horizontal position, or x, at the point of displacement, and the amount of time, or t, that the wave has been traveling. The variable in front of the sine function, a, is the amplitude of the wave, which is the height of the wave's crests and troughs. The last two variables are a little more complicated. The omega symbol is the angular frequency of the wave, and k is the angular wave number. The frequency of a wave is the number of waves that pass a given point over a period of time. Whenever you tune into a radio station, you're sorting them by the frequency of the radio waves they put out. Wave number is the number of wavelengths in a wave over a given distance. Angular frequency and angular wave number only differ from standard frequency f and wave number, or the nu bar, by a factor of 2 times pi. We can see this by comparing their formulas. Frequency f equals 1 over t. Angular frequency omega equals 2 pi over t. Wave number nu bar equals 1 over lambda. Angular wave number k equals 2 pi over lambda. In both sets of equations, lambda is wavelength and t is period. That's finally everything you need to know in order to find the displacement of a wave. It's quite a bit more than you might expect, but it's all necessary to deal with the harmonic motion of a wave. As a wave travels through a medium, it creates a displacement in it, which is a change in position of that medium from its starting position before the wave traveled through it. The wave displacement of a transverse wave is perpendicular to the direction of the wave's travel, as the material itself does not travel along with the wave. When we want to find the displacement the harmonic wave moving in the positive x direction creates, we use the following formula. Y xt equals a sine kx minus omega t. For a wave moving in the negative x direction, we change the subtraction sign in the equation to an addition sign. In this formula, yxt is the displacement. X is the wave's position on the same axis as the wave's movement at the point of displacement, and t is the time the wave has been traveling. The other three variables, a, k, and omega, are the wave's amplitude, angular frequency, and angular wave number, respectively. Amplitude is defined as the height of the wave's crests and troughs. Frequency is the number of waves that pass by a point in a certain time frame. Finally, wave number is the number of wavelengths that appear in a wave over a given distance.